Okay, so the density of Q and R and an introduction to sequence and series. So the density of Q and R is the first bit we're going to be talking about, and that's sort of a follow-on from the previous video. And it's a result that I wanted to prove because I think it's kind of a weird sort of proof when you look at it. It's not hugely complicated in it by any means, but it's just a bit strange, and a few things are done that, you know, they're mathematically right, but they all sort of come out of nowhere. So I wanted to walk you through it in a video. And then after we've done that, we're going to dive into sequence and series, which is sort of where the interesting stuff starts to happen and where real analysis really hits its stride. So what actually does it mean for Q to be dense in R? What we're saying, or what we're trying to prove, is that for all A and B that are real numbers, with A being less than B, there exists some R being an element of the rational numbers such that A is less than R is less than B. As is often the case, it's a bit of a mouthful, but all that's really saying is that between any two arbitrary real numbers there exists a rational number. So how are we going to go about proving that? Well, the first bit is whenever we see a for all statement, one of the really easy ways to prove it is to just let A and B be anything. Just not specify what they are, just let them be an arbitrary A and B, and then we can essentially neglect that statement till the very end. And then for this rational number over here, we can say R is equal to, say, P over Q, where, as per usual, P and Q are elements of Z, with Q not being equal to 0. Okay, we can impose the additional constraint that Q is actually greater than 0 and still be fine to define the rational numbers. And if you were writing out this proof in full detail, that might help sort of ease the language. But for the moment, we'll just assume that they're both elements of the integers. Okay, so we're going to start off by building two inequalities, and then we're going to manipulate them, and that this result should fall out afterwards. I'll just quickly rewrite this. P over Q is less than B. Okay, so that's essentially what we're trying to prove for arbitrary A, B, and Q. That doesn't really look like a Q, but anyway. First inequality that we're going to do is we're going to say that 1 over Q is less than B minus A. And now we can do that because of the Archimedean property. And the Archimedean property I didn't prove in the last video, but it was in the handout if any of you read that. And essentially it's just saying that we can do this. So we've done it. Geometrically, if you have the number line and you've got, say, A and B, all this is saying is that we're picking Q such that if you divide the number line up into little segments of length 1 over Q, then these segments, or A and B, are in separate segments. They're not in the same one, which hopefully makes sense why you can do that. The next inequality we're going to set up is that P minus 1 is less than QA is less than P. And again, that geometrically is fairly easy to understand. If you have a number line and you have, say, A, QA on the number line, we're just picking P to be the closest integer above it that's not equal to it, which we can do. Again, that's just a property of natural numbers. That's nothing unique to real analysis. So using these two inequalities, we're going to try and prove our top inequality. I'll quickly rewrite this one as A is less than B minus 1 over Q. Basic manipulation, that's using the properties that the real numbers form an ordered field. So we can manipulate inequality signs and stuff like that. Alright, so what are we going to do? First of all, really just straight off the bat, we've pretty much proved half of the inequality. A is less than P over Q. That bit there is just that part of the inequality there. And of course, we could always assume that whatever our rational number was, it's bigger than a. That's, not crazy. That's just properties that, the real numbers are bounded, or the real numbers themselves aren't bounded, but a real number, there exists, real numbers bigger than it. I think that might have been one of the exercises, but I'm not too sure. It's not a crazy property to get your head around, but anyway, okay, so we've proved the first part of the inequality. The second part of the inequality comes with a little bit more work, but we have p minus 1 is less than qa, so p is less than qa plus 1, not too hard. Then we are going to use this little piece of information here. A is less than b minus q, so p minus q outside of b minus 1 over q plus 1, which just becomes, when you expand it, which is again a property of the ordered field, you get p is less than qb, and that p over q is less than b, which is what we wanted to prove. That was the other part of the inequality, which we hadn't quite proved yet. Just quickly noting, this little bit here is supposed to be a less than or equal to sign, but it doesn't end up mattering because we substitute in something which is definitely less than. Alright, so I've got both parts of the inequality. We take the union, you get the idea. Not the most wonderful proof I've ever written out on a piece of paper, but hopefully it makes sense. But quickly, one of the things I found a bit bizarre about this when I saw it was it doesn't really feel like we're dealing with the real numbers. And I tried to make it so that you saw that we were dealing with the real numbers by talking about a rational field, or an ordered field, sorry. But there's tons of ordered fields. What makes this a unique property to the real numbers? How are we proving that Q is dense in R and not just proving that Q is dense in any, rational field, ordered field? And that really comes from this bit here. This assumption here, which we made, was based on the Archimedean property. And if you go back and look at that proof, the Archimedean property relies on the axiom of completeness, and that was the other part of our definition of R. So that's really sort of the crucial step in this proof, is assuming 1 over q is less than b minus a. And if it was any other ordered field that was lesser than R, we couldn't have proved this. Incidentally, you can write a fairly similar proof for the density of the irrational numbers in R, which I won't go through because this has taken, 8 minutes to do. But yeah, so we've successfully proven that between any two real numbers, there is a rational number. So rational numbers happen a lot. That's sort of the grand conclusion from that. Anyway, so that's done. The next thing that the book talks about, for any of you who are unaware, we are roughly following Stephen Abbott's Introduction to Analysis. The next thing the book talks about is cardinality, which is to do with sort of the size of sets and fields and stuff like that. And that is a really interesting topic, but I'm going to skip it. I might come back to it if it's of interest, but I don't entirely see the purpose of looking at it at the moment. It is important and it is interesting, but I think I'd like to sort of progress this series onwards to sequence and series, and then, integrals and differentials and stuff like that, because I think that's really what most people who sort of step into real analysis want to study. They want to get a stronger understanding of calculus. So that's what we're going to jump into now. We're going to jump into sequence and series. I'm going to highlight a problem, and it's a problem you would have come across in high school calculus and just sort of left and not solved. And I'm not going to solve it in this video, but I'd like to sort of highlight the problem as something that we can come back to, or something that we can have in the future and we can look at and we can go, oh yeah, that's something we're going to solve soon. And it's the problem to do with series, and the convergence of series, and why addition and just our basic operations don't work with series. So we're going to look at a really sort of classical example. -1, +1, -1, +1, -1, dot, dot, dot. And now we know from calculus that this doesn't converge. As much as, there's obscure places where we like to say it converges to some value, it just doesn't in the sense of calculus and real analysis. But if you look at it, it kind of feels like it does, because, I can group it. That's 0, that's 0, so we get -1 plus 0 plus 0 plus 0 forever. So doesn't that kind of just look like it's converging to -1? It's fair enough. If we group it in that way, it certainly is. But if we group it in this way, -1 plus 1 plus -1 plus 1 plus -1 plus 1, well, that's just 0 plus 0 plus 0. Well, now we've just sort of grouped it in a different way, but still under the finite sense, that would have been a perfectly legal thing to do when we've shown that it converges to 0. And -1 doesn't equal 0 last time I checked, so we've got a problem here. What about switching things around? So we can't group it, but what if we just switch it around? What if we try and bring one of the -1s out the front? So we have -1, -1, +1, +1, -1, -1, so on. Well, this little bit, that's -2, but this entire chunk here is just 0, and so's the next chunk. So now we've shown that it could be equal to -2 if we're allowed to switch it around. And hey, what's really stopping me from bringing 100 -1s out the front and showing that it's equal to -100? Or bringing 100 1s out the front and showing that it's equal to 100? It sort of appears that I can get this to equal really whatever I want. So one option is we just give up and say infinite series just don't work and ignore them and leave and not deal with them, but that would be, a non-mathematician's way of doing it. But there is hope. There is a sequence that does behave a little better, and that's a classical one. Another really common one that you'll see in high school calculus, and that's this one. The geometric series, but the geometric series with minus signs in it, or still a geometric series. And now if we remember back, this is of the form 1 plus r squared, where r is equal to -1/2. And if we remember when we were first taught series on geometric series, that's this sequence converges to 1 over, if it converges to 1 over, is it r minus 1, I think? Let me just check that. 1 over, it might be, hang on, that's wrong, it's been a minute. 1 over 1 minus r, I think it is. Yes, that is correct. Yeah, okay, sorry. So that sequence, if we plug in r equals 1/2, we get 2/3, which is approximately, 0.66, etc. Not really approximately if I put the ... but you get the idea. Alright, no different to the one above. We've shown it converges to a particular value, but we haven't used any grouping. So if I do group this, it's not going to change anything. I'm still going to get it converging to the same value. But what about if I start rearranging things? What if I do 1 which is the one I checked on my calculator? It was 1 plus 1/4, minus 1/2, plus 1/16, plus 1/32, minus 1/8, so on and so forth. So we have 2 positives, a negative, 2 positives, a negative. And I don't know how to deal with that with the geometric series, but it looks about the same thing. If you plug that into your calculator and evaluate the first few dozen terms, you again get about 0.66. So it looks like, we haven't proven it, but at least appears in this case in blue, we can group things and we can rearrange things and there's no problem with convergence. But in the case in red, we can't. So how do we know which ones we can and which ones we can't rearrange and group and stuff like that. Because rearranging and grouping is really sort of our basic algebra. It's what we've relied on since, the early days of our more formal math studies. We've always sort of needed to group things and rearrange things. It's been really core, and we've just shown that under particular circumstances we can't. So it would be really nice to know when we can't rearrange things and when we can. And that's what we're going to be looking to eventually prove or eventually find an answer to after all our work, but it's going to take some work. And before any of that work can start, we need some proper definitions, because that's really where the breakdown happens. The breakdown in calculus, and the reason real analysis exists is because calculus was made, a few hundred years before, and it was lacking a lot of rigor. So real analysis imposes that rigor, and it allows us to answer these questions of when and when we can't rearrange a series. So that seems like a good spot to start. We'll write down a few definitions. The most obvious definition to write down is going to be the definition of a sequence. So a sequence is defined as literally just a function where the domain is equal to the natural numbers. That's all the sequence is. It's a function with the domain over the natural numbers. And now our conventional notation is that f of n we write as a of n, and that the entire sequence we write as a of n in brackets. That's the notation I'll be following. Some people use different notations, but it's kind of the easiest notation to write. So then what's a series? A series is just the sum over n of a sequence from n equals 1 to infinity, 1 being our first natural number. So a1 plus a2 plus a3, so on and so forth. But a series, it's nice, but we want to find a way, and it'll be quite beneficial to represent a series in a slightly different way. We actually want to end up representing a series as just a special type of sequence. So what we do is we look at the partial sums, and we let S1 be equal to A1, and S2 be equal to A1 plus A2, and let Sn be equal to A1 plus A2 plus ... up to An, and then we're looking at the sequence now of S of n, and wrong notation. We're looking at S of n, and we're looking at what it converges to. So now we've managed to make a series just look like a sequence, and they essentially end up being the same thing. And a sequence is, from sort of an introductory standpoint, it's a lot easier to deal with than a series, because you can get rid of that addition, at least sort of in an abstract sense. Okay, but I just mentioned convergence, so that seems like a good next spot to talk about. Definition of convergence. So again, it's a definition, and these pop up a lot in real analysis. Real analysis is all about definitions that intuitively seem right but are really well written. So A of n converges to some value A, right? Which again, if we're talking about our sequence, then our sequence converges to a value of S by this exact same definition. If, I think it's an if and only if statement, but for caution I won't write the other end of it. If for all epsilon greater than, that's not an epsilon, that's a 3. If for all epsilon greater than 0 there exists an n being an element of the natural numbers such that a minus a capital N is less than epsilon whenever n is whenever our capital N is greater than our little n. Again, one of those definitions with lots of quantifiers and stuff in it looks a bit confusing, but all that's saying is that if we pick some number, some real number, real positive number, then there exists a point where beyond that point, all of the numbers in our sequence are close to A. So if we draw that out, say we have our number line, and say A1 maybe over here, A2 over here, A3, A4, A5, you get the idea. And say we're trying to prove that it converges to that point A, then if we pick a value of epsilon, again, absolute value of A minus AN is just going to be that sort of region, then all of our points, A3, A4, A5, A6, so on and so forth, lie within that region, and we can find a point in our sequence where all the points beyond that point lie within that region. And that kind of brings light to a slightly different way of phrasing it, a more topological way of phrasing it. And that's to do with a neighborhood. So for those of you who don't know what a neighborhood is, V epsilon of A is called the neighborhood of A, with, sort of radius epsilon is defined as being all x of the real numbers with x minus A being less than epsilon. So it's just all the numbers that are within a finite distance epsilon away from that point A. As I said, it's called a neighborhood, and as kind of highlighted up here, we can redefine convergence in terms of neighborhoods as the sequence AN converges to A if there exists some point, I don't really know how to write this without just saying it, if there exists some point N, I suppose I can put an exists there, some point N, where beyond N, all of the numbers in the sequence lie within that neighborhood. And I don't really know how to write that, but it'll be in the handout, properly written out. I don't know how much sense any of this is making, if I'm being completely honest. It's been a bit of a weird one. So I'll just try and run through everything we talked about again, because it's been a little bit sporadic. It's been one of those videos just like the first one where we're trying to get definitions down, and it's been a bit hard to get all my thoughts on paper. But anyway, I'll pick white. We started off by talking about the density of Q in R and how between any two real numbers there exists a rational number. So we proved this inequality here. We proved it in a bit of a bizarre way, but we assumed two other inequalities to be true. We made those assumptions because of the definition of the real numbers and the Archimedean property, which is a consequence of those. We did some algebra and we showed that the inequality was true. And all that means is that the rational numbers occur quite frequently, to say the least, within the real numbers. Then we started talking about sequence and series, and we talked about a major problem, and that's to do with how when we group things in different ways within an infinite series, we can end up with different results, and how if we manipulate and switch terms around, we can again end up with different results. But there was a little bit of hope because there did exist particular series where we could group it in particular ways and we could rearrange it and we would still get the same answer every time. So once we'd illuminated that, and we've talked about how we want to come back to that at some point, we started making some definitions. We defined a sequence as just being literally any function with a domain over the natural numbers. We defined a series as being the sum of the terms within a sequence, and then managed to define a series as a sequence through what are called partial sums, which were these guys here. Then we defined convergence in a kind of bizarre way, but we just said that a sequence converges if after a certain point all of the numbers are within a certain distance of each other, or within a certain distance of that point we're trying to say it converges to. We talked briefly about neighbourhoods, which are a sort of topological idea, and we kind of redefined convergence in terms of neighbourhoods, but it was a bit wordy, and it will be properly written out in the handout. Yeah, I hope that made at least somewhat sense. It is really just getting definitions on the table so we can actually start to use them later on. But yeah, thank you.